Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. The first known ransomware attack took place in 1989. Yes, 32 years ago. A PC virus would hide and encrypt the file name, though not its contents, of all the files on an infected machine. After this process was complete, the virus would demand they pay $189 US to obtain a repair tool. That's a small price to pay compared to the sums asked for modern malware attacks, which encrypt the entire contents of your files, effectively locking you out from them. Any serious IT organization needs to be panicked about this attack vector and looking for ways to detect and thwart it. How can signals at the hardware level give an indication of when your system has transitioned from its stationary usage into a sequence of operations suggestive that an attack could be underway? Today on the show, I speak with Nitin Pundir about techniques for detecting crypto-ransomware.
Hi, Kyle. Thanks for having me. My name is Nitin Pundir. I'm a PhD candidate at University of Florida. I work in the Florida Institute for Cybersecurity Research under Professor Mark Teranipur. And my specialization is in hardware security. And we look into security solutions which can utilize machine learning. So basically, we try to develop machine learning-based hardware security solutions.
Well, you said you're a PhD student. Have you picked your thesis topic and title yet?
So basically, I know what I'm supposed to do. The topic is not finalized yet. So basically, I'm working on developing machine learning-based secure physical design solutions for side channel attacks. But that is not this paper is about. This paper is about something else. But yeah, my dissertation will be on using machine learning to enable the secure physical design that can allow pre-silicon based side channel verification for the CAD companies like Intel, Synopsys, and for the government chips and so on.
Oh, that's very interesting. Yeah, maybe we could take a moment there before we get into the paper. That's not something I'm familiar with. Is this new cutting edge stuff, or are you just pushing it forward?
So it's a new cutting edge stuff. So you must be aware of side channel vulnerabilities like a power side channel. There was a Spectre and Meltdown, right? Which create like huge buzz because all the Intel architectures were like vulnerable to it. So basically what happens is like all the chips which are manufactured, there is like a lot of engineering effort before it gets fabricated, right? Because once you get a chip, it's like finalized. You cannot make any modifications to the hardware. So there is like a huge deal of verification going on in the back end, like even before the chip gets fabricated by TSMC or other global foundries, right? So during that verification efforts, they try to make sure that there are no hardware vulnerabilities in the design, right? Such that like the design is not vulnerable to like power side channel, laser fault injection attacks, and so on. But what happens is current verification efforts are like limited, right? Because you need to have the physical characteristics to make sure your design is not vulnerable. Because what you're trying to say is after fabrication, your chip won't be leaking any of these side channel vulnerabilities, but your chip is not fabricated yet, right? It's just in the pre-silicon area. So my effort comes into that. So basically, we are providing all these CAD industries with these verification frameworks where you can kind of emulate the post-silicon environment in your pre-silicon test framework to make sure that your design or your chip layout is not vulnerable to these like side channel vulnerabilities. And that's where my dissertation is more focused towards.
Well, exciting and important stuff for sure. Well, the main paper I wanted to invite you on to talk about is titled RanStop, a hardware-assisted runtime crypto-ransomware detection technique. For anyone who's not familiar, I think most listeners will at least be aware of crypto-ransomware attacks. How could you not? But could you give a high-level summary for what's happening there? What are the security holes that allow such a massive takeover to happen in an organization?
Basically, what happens is these kind of attacks were like very prominent, right? Everyone has heard of it. And recently in Florida, they attacked the pipeline, right? And the entire like database was sabotaged and they were asking money like a ransom in like Bitcoin and everything, right? So what happens is like the attackers kind of exploit some like loopholes in your system and they get access to your system, right? Once they get access to your system, they start encrypting your files and database and everything. And in turn, like in return to give back access to those files, they ask for some money in terms of all these cryptocurrencies, which are like untraceable and everything. So since these attacks are kind of which sabotage or like make hostage like all your data files, like critical files, especially in like government agencies, like the pipeline and even in hospitals, because these areas are where which are like most vulnerable because these people don't come from like the cybersecurity background and so on. So their systems are kind of more exploitable and they have like more critical data to save, right? So that's where the ransomware and everything is like very critical when it comes to all these institutions which are handling all the critical user data, right?
Absolutely. A lot of organizations have turned to software solutions for this, and it kind of fits with the way people are thinking, right? We've had virus checkers for a long time that are all software-based. Why is a hardware-assisted runtime a good solution for this problem?
If you talk about the solutions, right, like all the antiviruses and everything, they are software-based solutions, right? So basically how they work is they already know the malware or the ransomware, which is already there. They try to extract the software-based signatures out of this, right? And based on that, they kind of perform the signature verification when you try to run something on your system and say, hey, this is kind of template matching. And then they say, hey, this signature belongs to a virus, so it should not be run. But what happens is all these attackers, they're also very smart, right? They apply changes to their malware in such a way that the signature changes and all of these antiviruses and everything, they are not able to detect those. And so basically, if you see in overall, all these software-based verification methods, they're not applicable to zero-day attacks, right? Like new variants of, I'll say, crypto-ransomwares, if an attacker changed those and just spread those in the network, maybe these software-based applications won't be able to detect them on time. So basically what we plan to do, like we aim to do, was extract the hardware features, basically like a signature. So it will be like analyzing someone's handwriting and then analyzing different ways he writes the email and so, but the key characteristics of that person, like the handwriting, remains the same. So basically that way, by analyzing the hardware-based microarchitectural events of these ransomwares, we can protect against the zero-day attacks, which will be like really helpful.
When I think of a hardware approach, in my mind, I'm thinking of something very low level. You know, the code I wrote, maybe it's in Python, perhaps somehow got converted down to C and then to assembly language, or there's operating system libraries involved. And then on the hardware, it's just bits going through integrated circuits. It seems very low level and almost like it would be difficult to recognize malware from ransomware. You were talking about the handwriting. What does handwriting look like at the binary level?
When I say the hardware events, so it's like, as you said, we are literally going to the lowest level possible, right? So what we exploited in this case, or like took advantage of, is all these hardware performance registers or counters provided by the architecture itself, right? So these performance counters are actually used by the developers to see the efficiency of their code, right? Like this particular section has a bottleneck or something, right? In terms of cache misses or the branch executions and so on, right? So we took advantage of those hardware performance counters and extracted these metrics. So some of these hardware metrics include like branch rate, branch miss prediction rate, cache misses, L1 miss rate, and so on. So there are like a bunch of these micro-architectural events which are like out there and could be utilized.
Very interesting. The branch rate, if I understand that correctly, at the assembly level, branching is really like an if statement. I guess at a higher level, it's, if this is true, do this, otherwise branch to some other location. And it seems like code should be free to branch or not branch whenever it wants. Going into it, what led you to believe that could be an insightful metric that would help tell the difference between some of these different types of software?
Basically, when we were planning on developing some of these features, right? I not say features, but a technique which could exploit the hardware microarchitectural events. So what we had in our mind was that a program does not change its semantics over a variant. So basically, if you see a crypto ransomware, right? What's its basic characteristics, right? So it's going to search for all the data files in in the user directory or in the system and start encrypting it, right? So that is like a very basic characteristic. And if you try to extract the microarchitectural events of this behavior for a crypto ransomware, you will find some similarities. Making sure of these similarities by naked eyes will be like very difficult, right? So that's why we try to exploit the machine learning in this case. So where we have bunch of these microarchitectural events captured from different ransomwares and the benign programs, and then we say, hey, this is my machine learning model. Can you identify some similarities between the ransomware variants and different ransomware programs? And can you forecast it or classify it so that, my model can distinguish between the ransomware and a benign program?
And then does that end up being a supervised learning technique?
So at this point, this was a supervised learning. So we already have bunch of ransomwares from a database from VirusShare. We have bunch of benign programs, and we had to be especially careful because I was running this ransomwares in my university. So I had to tell my IT administrator, hey, keep monitoring my port. If something suspicious happens, make sure it does not, get away into the entire university network.
Oh, that's an interesting challenge, yeah.
And actually it did. So he said someone was scanning ports from my network. And I said, I was not doing that. Probably something escaped from virtual machines and was doing it.
Oh, wow. Well, yeah, then, so to do that, you need some labels. You'd mentioned that there are, some famous ransomwares out there. What do you start as for your control group? There are some benign software applications. What's the sample there for comparison?
Basically, when we were choosing the benign softwares, right? So we wanted a mix of benign software. So like normal applications like opening a text editor, writing, like copying, moving, and all those. But also we wanted some benign programs which have similar characteristics to a crypto ransomware, right? Where you are encrypting a very large file, or where you're decrypting a very large file, where you're deleting a very large file, because all of these characteristics are kind of similar to ransomware, crypto ransomware. And we wanted to have a mix of that database. We wanted to check whether the machine learning would be able to identify microarchitectural events from these two databases, which are very similar if you see from a human perspective.
Thanks to this week's sponsor, Oval Edge. Oval Edge is a cost-effective data catalog designed for end-to-end data governance, privacy compliance, and fast, trustworthy analytics. Every business has personally identifiable information, or PII. Not only do you owe it to your users to be good stewards of their data, it's going to be required of you as stricter and stricter privacy laws come into play. The good news is you don't have to take care of that solely on your own. You can call the experts at Oval Edge. Their end-to-end data governance suite has flexible solutions at a fraction of what other providers charge, starting at $100 per user per month. Their data cataloging solution uses artificial intelligence to crawl through all of your data sources and identify the parts that have PII. You know this isn't a simple problem. It's not just a matter of a couple of fields in a user table. PII is scattered throughout notes fields and other subsidiary tables and places. It's copied, it's migrated. If you really want to protect your customers, you need a powerful tool like Oval Edge. CDOs, CPOs, CIOs, and any leadership in data, I want all of you to head over to ovaledge.com/dataskeptic. There you can download and implement their data governance guides, or even schedule a demo if you want to learn more. That's ovaledge.com/dataskeptic. Are there any concerns you had about false positives? I could see where the Dropbox application could be flagged because it's deleting or moving a lot of files around by design. Or maybe if I'm going to encrypt some documents, the process of encryption might look like what the ransomware is doing. Could normal operating systems be flagged as ransomware when they're not?
Actually, yes. So when we were developing this method, right, so that was the biggest challenge. Your false positives and false negatives are like two metrics, right? So basically, when we are training the model, generally everyone sees as the accuracy of the model, right? But in this case, more than accuracy, it's important that we divide that accuracy into false positives and false negatives. But if you see from like a user's perspective, right? If there is very high false positive, it means that a benign program is characterized as a ransomware. And then he will just have to go and say, hey, this is not ransomware, allow it to execute. And then there is false negative, where ransomware is characterized as a benign program. In our opinion, the false negative is most dangerous because you don't want even a single ransomware to slip by. Whereas a high false positive can be okay. It will just be bothersome to a user, right? He'll just have to go and say, allow it, but at least his files will be safe, right? So that's why in our method, we try to reduce the false negative, but we were fine with our false positive. So if you will see like in the paper, the false positive is like kind of in the range of 15 to 20%, right?
Well, you've talked a little bit about some of the features that the machine learning algorithm will train on, but they're kind of interesting features like deleting a large file. I suspect a lot of the listening audience would not know how to go implement that themselves. Could you talk a little bit about the tools you use to get access to these seemingly low-level features that you're going to train on?
How we did was, so each core has a hardware performance counter, and all of these are capable of collecting the microarchitectural events. But because of the limitations, only 4 or less than 4 microarchitectural events can be captured at a time, right? So basically, what we did was we used the software such as Liquid, which can go and integrate into the performance monitoring unit in the system, and it's provided by Intel. And then basically it allows you to capture the microarchitectural events based on different groups. So these groups could be branches, cycle activity, data, flops, caches, L2 data, and so on. So if you go and see in our paper, there are like 16 different performance groups, which in turn has different metrics. For example, branch has 4 different metrics: branch rate, misprediction ratio, instructions per branch. So that is about how we collected the microarchitectural events. The another thing was, these are ransomwares, right? So we had to be like very, very careful in where we are running this. So what we did was we spin like a virtual machine. So all of these ransomwares were like for Windows. So we spin a virtual machine, run the ransomware, collect the microarchitectural events, delete the entire machine, and bring it back to the previous state where it was before running the ransomware. So we had to do it like continuously for all different executions. And the problem, I mean, it's good. It's kind of replicating how a normal user will work, right? Because there are multiple things happening, like different processes and everything is like running in the system, and at the same time ransomware is running. And in this case, virtual machine is running, different processes inside that virtual machine are running in their normal execution, and on top of that ransomware is running, or a benign program is running, and we are like hooking up the performance monitoring unit from outside the virtual machine and collecting the microarchitectural events. So interesting thing here is like, so what we are collecting are coming from CPU directly, like from the core. There is like lots of noise. So there's a host machine, which is Linux, and then there's virtual machine, which is Windows, which is running the ransomwares, and all these microarchitectural events are collected. So basically we had to do it so that, you know, if the ransomware even escapes the virtual machine, it will have an unfavorable environment in the Linux so that it cannot go into the network.
Is there any overhead to be paid for the collection of all these?
Oh, yes, there was like a lot of overhead in terms of collection, since we had to delete the entire virtual machine and like copy the new virtual machine back to its previous state. That was time consuming, like so much time consuming. Then there was this, you can only record like 4 microarchitectural events at a time. So to collect more microarchitectural events, the same ransomware had to be run multiple times with different performance group attached to the PMU. So it was like a repetitive process, and it took us like a long time to collect the data set. And even if you see from the machine learning perspective, this is not a huge data set, but from the hardware perspective, it took so much time to collect that, even this small data set.
Yeah, so once you've collected it, in my mind, you can represent that as a time series. It's the history of the events, what the event was and when it happened, which is great because it's sort of all the raw data. It tells the full story and you can replay the history if you want. But there's kind of a logical leap to go from that raw data to something a machine learning algorithm, or at least maybe today's machine learning algorithms, know how to process. Generally, you have to do some aggregation or feature engineering or something along those lines. Are there any steps you had to do before the data became useful for ML?
What we had in mind was, if you see, we don't know what these different ransomwares were doing in the back end, right? Because we just had these raw ransomwares from the database and we were running. And our objective was, in a limited time frame, which in our case was 20 milliseconds, we should be able to detect whether this is a benign or a ransomware. The thing is, the ransomware may or may not be encrypting or sniffing around the network or searching for the files at those particular time instances. Could be just lying there dormant for a while and then start searching. There is like the context switching, where basically that process is not scheduled by the CPU, so we don't know at what time instance that process was running, but we know within this time period there are certain time instances where the data is important. So that's why we wanted the model which could have the past memory and have the right memory, but which is also insensitive to the time intervals. So that's why we chose LSTM. And basically, to process the data, we just normalized the data, because basically it's like we knew the data is there. I mean, the key features are there, but it's like if we try to manipulate the data, we may lose some of the features. So that's why we did like the least minimum pre-processing as possible and let the LSTM layer try to extract the features. And then we perform the global average pooling to reduce the dimensions so that our next fully layer can actually extract the important data from all this like multi-dimension time series we have.
Today, many small business owners are busier than ever. Time spent searching for and interviewing the wrong candidates for a job opening could be time better spent growing your business. That's why LinkedIn Jobs has made it easier to get to the candidates worth interviewing faster. And it's free. Create a free job post in minutes on LinkedIn Jobs to reach your network and beyond to the world's largest professional network of over 750 million people. Focus on candidates with the skills and experience you need. Use screening questions to get your role in front of only the most qualified people. Then, use the simple tools on LinkedIn Jobs to quickly filter and prioritize who you'd like to interview and hire. I have personally followed that simple advice and been very satisfied with the experience. Whenever I'm hiring, especially for an important role, LinkedIn Jobs is always one of the places I think to go to, top of list. Everyone's on LinkedIn, and I've always been satisfied with the quality and volume of candidates I get. LinkedIn Jobs helps you find the candidates worth interviewing faster. Did you know every week nearly 40 million job seekers visit LinkedIn? Post your job for free today at linkedin.com/dataskeptic. That's linkedin.com/dataskeptic, all caps, to post your job for free. Terms and conditions apply. Ah, very interesting, yeah. And makes sense why you would choose those architectures. Were those, broadly speaking, inspired by other techniques, or did you really have to come up with something novel for this use case?
We knew in the past people have used, so basically we knew people are using hardware performance counters for the malware detection and so on. There have been some techniques in the past, but when we were doing this, so we came up with the LSTM. We knew the hardware performance counters are important. We came up with the LSTM based model, but at the same time there was another paper published who also used the LSTM based autoencoders for malware detection. We and that paper kind of published at the same time. So that was interesting.
Yeah, very interesting. Great minds think alike, I guess, sometimes. Well, let's talk about the results. We mentioned already that you were framing it in the context of false positives and false negatives. Could you share some numbers with us? What sort of statistical achievements did the model turn out getting?
This was our preliminary results, right? So because the data set is small, right? And if it has to be, done on a large scale, like to be adopted by industries, right? Like antivirus companies, there need to be very large data set, and the models need to be like retrained with new variants and so on each day, right? Because they need to learn. So with this, even with the small data set, we were able to like achieve around 80 to 90% accuracy in terms of classification. So at this point, the model is purely supervised classification, but we also envision that this could actually be upgraded to forecasting as well. For example, like by understanding the microarchitectural events of program for a certain amount of time, you can forecast like how microarchitectural events will look like in the future. And based on that, the model will be able to say that whether it is a benign or a ransomware. So that is like a next part of the research. But again, even with the limited amount of data set we were able to generate and everything, so on an average we were able to achieve 80 to 90% accuracy. The false positives with 70% training data were around 20 to 15% for most of the branches, like for most of the performance groups, and false negative were around 1 to 2%. So basically it allowed like very few ransomwares to be classified as benign, but it was able to detect most of them.
So we've been talking about these lower level features, things like essentially measuring what the CPU is doing. Even though I understand intuitively, like, okay, ransomware is going to maybe be encrypting more than other programs, it doesn't obviously follow for me how a model would work, what it would look at in those features and what it would consider in making its decision. I guess you're closer to the data though. Do you find the resulting model interpretable? Can you understand the mechanism of it? Or is it just kind of a black box?
So machine learning is usually kind of a black box, right? So we tried to see the data set, right? I mean, to me, like to the naked eyes, the data set kind of looked similar for the benign and ransomwares. But obviously, if you try to separate, machine learning is obviously seeing something else, which humans obviously cannot see, and they were able to identify something. Because you see, like the LSTM, what LSTM is doing in this case is keeping track of the past features as well, right? So basically the processor is scheduling different processes. It's not like the ransomware is always executing on the CPU core, right? Other processes can also come in. So basically the events which you are collecting is noisy, right? But LSTM model is having a past memory of some events, and combining all of these, it's creating some like new features which obviously the human is not able to perceive, and that's how it's able to classify between the benign and the ransomwares.
If I were an IT administrator, or maybe I oversaw a data center, something like that, I would be chomping at the bit to get your software into my industrial application, because the features you're looking at, they don't invade privacy. They're fairly, agnostic to what the program is and that sort of thing. I would love to get this on all those machines and then have some indicators about whether or not, there seems to be a ransomware infecting my system. How far away do you think we are from this being an industrial application in that manner?
So there was a conference in our university, and Intel actually presented the paper and their work on exactly similar things. So they are looking into using these microarchitectural events, which they have already embedded different sensors into the CPU, and collecting data from that to provide the security. So industry is already doing research into this field, and soon probably will have some, real life application coming out.
And when that comes, of course, there'll be a cat and mouse game. I maybe hesitate to ask this because I don't want you to give them too good of advice, but once the malware and ransomware creators learn about these techniques, do you think there are avenues by which they can avoid them?
So obviously hackers are smart, right? So they are like always 1 or 2 steps forward than the verification or the security engineers, because what they need to find is one loophole. And as a security verification engineer, we have to close all the doors, right, for them to come into. I mean, I'll say it will always be a race, where we are trying to protect, and all they need to find is one loophole. And systems are very complex and they're getting complex and complex. So let's have our fingers crossed.
For sure. You'd mentioned a couple constraints on this, like having the setup with the VMs and doing this properly in a secured way has, an overhead, resulted in a small but still promising data set. So there's lots of ways this could be scaled up if the right investment was put into it. What do you think are the most fruitful directions this should move in the future?
That's right, actually. So because this data collection and everything, if you see, when it comes to providing machine learning based solutions, the major constraint is the data set, right? So you need to have a really good data set to make sense out of it. And the industries like, the current antivirus industries, the companies, I think they are already investing into this direction, providing machine learning based solutions. But yes, if they invest more and collaborate with the universities and so, we could have a really good data set and we could rapidly ramp up the development of such mechanisms or the frameworks where we can protect against the zero-day attacks. Because I think machine learning is the only thing which can kind of forecast or classify for something which is not already present and provide protection against these zero-day attacks.
Absolutely, yeah. This is a very modern and real threat to the world that we need solutions for. Well, Nitin, where can people find you online?
If you go to the University of Florida and search for FIX Research, which is short for Florida Institute for Cybersecurity Research, you will see me as one of their students. And also, if you search me on LinkedIn, you can find me. And this paper is already on archive and my email ID is available there. If you literally search Nitin Pundir UF, I'm pretty sure you can find me.
Awesome. Well, we'll have some good links in the show notes as well. Thank you so much for taking the time to come on and share your work. This is extremely interesting stuff.
Thanks, Kyle.
That concludes another installment of Data Skeptic Time Series. Our guest today was Nitin Pundir. Our sponsors, Oval Edge and LinkedIn. Myself, Claudia Armbruster, as associate producer, Vanessa Blyde as guest coordination, and our host, Kyle Polich.